Hello all. In this video, we're going to take a look at heuristic-driven search algorithms, in particular greedy best first search, which is kind of it's less practical than kind of an interesting little anomalous thing. And we're also going to look at A star, which is the algorithm everybody loves the best. And we're going to compare those to the lowest cost search, least cost search, whatever we want to call it. Because I want you to see that they're fundamentally the same algorithm. And when we actually implement them in the code that we're looking at in a little bit, we use the same underlying algorithm, and we just change a few important surface details to change it from one algorithm to the next. So these are informed search algorithms. They are incorporating a heuristic into how they calculate costs. But we'll take a look first at the pseudocode, and then we'll come back and talk about them at a high level. All right, so I'm starting with the pseudocode for lowest cost first, which we talked about in an earlier video. And what I've done here is I've re-highlighted a few things, including highlighting in yellow specifically the cost calculations. So you remember lowest cost search. It uses a priority queue to organize the fringe elements so that it can always select the fringe element that has the lowest cost built up so far. So when we start with the start state, typically that start state has a cost of 0. And when we generate children of a particular state, we update their cost to be their parent's cost, that's this part right here, plus the cost that is involved in getting from the parent to the child. So the child's cost overall is the sum of all the costs from the start state to that child. That's how lowest cost search works. There's no heuristic involved here. But the fundamental of this best first search is the idea of a priority queue with a cost associated with it. And so when I look at the other two algorithms, greedy best first and A star, what you'll see is that they are identical to lowest cost search, except in how we calculate the costs that govern the priority queue. That's what makes them different from each other. Lowest cost search, it's all about the cost that has happened so far, the actual cost we have seen from the start to the current state. Now, if I look at greedy best first search, what you'll see is that it's doing something different. Everything else is the same, but the cost is calculated differently. So we talked about heuristics in the earlier algorithm. What greedy best first search does is to ignore the cost that is accruing so far. It doesn't care at all about how much cost has happened between the start and where it is. It's making its decisions entirely based on the estimate of how far away it is from the goal. So it looks at all the frontier elements, all those fringe elements, those leaves of the search tree, and it finds the one that has the lowest heuristic value, and that's the one that it picks next to explore. So that's what this pseudocode is saying. The cost is H of the start state. H stands for your heuristic. Now, there are a bunch of very mathematical people who came up with these searches, so they did a lot of stuff that is using more mathy notation, as you'll see when we get to A star. But for H is easy. H stands for your heuristic. So we imagine there is a function, we pass it a state, and it reports the cost, the estimated cost from that state to the goal. Nothing about how much it costs to get to that state. Only in isolation, cost from state to goal. And you can see when we do the frontier, when we look at a child, when we calculate its cost, it is solely based on the heuristic between that child and the goal. It does not in any way incorporate costs related to its parent. So greedy best first search is ignoring what the cost that's happening. It's just trying to pick the one that looks currently closest to the goal every time. That's what makes it a greedy algorithm, is it always picks the one with the heuristically lowest estimate to the goal. It also makes it somewhat chaotic. And as I talked a bit with some of you, but not with everyone. The nature of this algorithm is that in certain contexts, it's terrible. You put it in our terrain world, where some squares in the grid are low cost and some are high cost, but the agent can pass through any of them. And this algorithm is very likely to just march straight across a mountain to get to the goal, because it doesn't pay any attention to the actual costs in the squares it's visiting. It only pays attention to the heuristic cost. How many steps away from the goal is that location? But if you take greedy best first search and you put it in a world that's mostly open, but maybe with some obstacles, it can be much faster at finding a path to the goal than the other algorithms like least cost search and A-star search. It's much more akin, it's like a long-eared jackrabbit compared to the rabbit in the hare in the tortoise and the hare. It's a cousin of depth first search. It's impulsive, it goes zooming towards the goal. If it finds an obstacle, well, yeah, it'll backtrack and try a different path. That may get you a reasonably good path very quickly. It will not necessarily get you an optimal path. Much like depth first search, it can give you disastrously bad paths, depending on what it does. But it does tend to head directly toward the goal. Put it in a maze and it's hopeless. But mazes are hard for everything. All right, so that's greedy best first search. As I said before, this is not one that everybody uses all the time, but it's nice to know it because it might come in handy once in a while. And it certainly, under certain circumstances, will do much less work than some of the other algorithms. It's just that it's not going to give you the optimal solution anyway. A-star is everyone's favorite search algorithm. It's like the one that tries to balance what least cost search is doing and what we're doing here with greedy best first. It puts those two together. So it pays attention both to the cost that has accumulated so far and to the heuristic that goes to the goal. So in some sense, it's trying to estimate the total path cost. It's just that as it moves forward, it knows more of the path, so it can be more and more accurate about the total path cost as time goes on. What does it look like as an algorithm? It looks exactly like least cost search or greedy best first search, except for the yellow bits. So there's some complications with A-star that I'm going to talk about. I may go back to my notes for this. But fundamentally, the only difference is in how we calculate the cost. So here's where mathy people stepped in and they're like, oh, we have H for heuristic. Well, let's use F and G because those are the other two labels that we give to functions, F, G, and H. Those are like the three. So we'll use those. Maybe there was something more behind it. I don't know. I wasn't there. I just know that these have specific meanings in the context of A-star, and you just have to memorize what they mean. So H of the start state, that is the heuristic estimate of the distance from the start state to the goal. What is G? G is the distance we have discovered from the start to this state. G is what least cost search uses. The G cost is the least cost search cost. So it's how much it costs to get from the start to where we are. And then we add to that the heuristic estimate of how far it is from where we are to the goal. And you can see that what we're doing is saying, well, if I go through this state, roughly how much is it going to take for the overall path? So the costs associated are always about the overall path. Start to this state to goal. And we use F to mean the sum of those two, the total cost. F is the value that actually goes into the priority queue and that is used to order the values in the priority queue. The sum of the G cost and the H cost, the cost so far and the heuristic estimate. I wrote that down here in kind of a cryptic comment just so you could see it. We will walk through examples that hopefully will help to illuminate exactly how this works as well. One of the complications of this is in order to calculate the G cost for a child, we need to know not the F cost of the parent, but the G cost of the parent. And that means when you actually implement this, you need to keep the G cost, at least keep the G and the F. You could keep G and H and calculate the F cost, but you need to have the G cost stored and available, or something that you can recalculate, however it works out, because you absolutely have to have that as well as the total of the G plus the H. I'll try to talk about that a little bit more and hopefully make more sense of it. All right, so here's just a summary, just recapping what we were just talking about. Least cost first. The priority value is the cost of the path from the start state to the current state, which is the G cost. Greedy best first search, the priority value is the heuristic cost from the current state to the goal, which is the H cost. And A star, the priority value is the sum of those two. It's the G cost plus the H cost, so you're taking into account both parts of the path. It is possible. I said we can prove. Yes, we can. We are not going to, but yes, we can. It is possible to prove that A star will always find the optimal solution so long as the heuristic for the H is optimistic, so long as it never overestimates costs. Let's take a look. Let's take a look at greedy best first search. All right. We are now going to look at the sliding tile puzzle once again, and we'll think about it in terms of heuristic search, and we'll look at greedy best first search and then A star and how it looks on these. So we have the same example that we were doing before, a nice short example. You just need to move the 4 up and the 7 and the 8 over and you got the solution. So it's only 3 steps away. That's good for us because it's just a simple example. What are we going to use as a heuristic here? Well, let's take a look and see. We're going to look at greedy best first search. Here are a couple of criteria about it. It doesn't revisit states that have been explored. It starts with a starting state and it chooses based on the heuristic cost. It only keeps 1 copy in the frontier set. That's just like least cost search. The heuristic cost is the number of non-blank tiles that are out of position. So in this case, 1, 2, and 3 are in position, 5 and 6 are in position, 4, 7, and 8 are out of position. So this particular configuration will have a heuristic cost of 3. It will take at least 3 moves to get this into the correct solution. That actually turns out to be accurate, but it would be less accurate for a more complex puzzle. All right, so much like least cost search, when we do this, we need to keep very careful track of the costs of the leaves. So I'm going to draw this out as a search tree, but we'll just attach the cost to each node so we can choose the lowest cost leaf each time. So when we start out, the cost to goal is the H value of 3. So we visit that node first. It's now explored. It'll never be visited again. We generate its 3 neighbors. So moving the 1 down, moving the 5 over, moving the 4 up. And what we do with that is we then calculate the heuristic cost. So here, 2 and 3 are in place, 1 is out, 5 and 6 are correct, 4, 7, and 8 are not. So we have a total cost of 4. That's our heuristic value. Similarly, when we move the 5 over, now 5 is out of place and 4, 7, and 8 are still out of place, so we have a total cost of 4 again. If we move the 4 up, only 7 and 8 are out of place, so the heuristic cost drops. that means we will choose this child as the option for the next step. So that looks pretty good. We only have one option here, which is to move the 7 over, but notice that our heuristic value drops again because we are in fact moving pieces into the correct position. So we choose this the child of number 2 as our number 3. It has 2 neighbors. We either can move the 5 down or the 8 over. Moving the 5 down leaves us with the 5 and 8 out of place. That's actually an increase in the heuristic cost. Or moving the 8 over takes our H cost to 0, so that goes to the front of the priority queue. And the next round, it is selected, and we know we're done. Yay! Good things happening there. That's greedy best first search. Now what I'm going to do is go back and look at my notes a little because the next one to do is A star, and we're going to talk through what A star does again just a little bit before we look at the example. All right, A star search. Some things that we know about it: it's optimal. It should always do no more work than least cost search. It may equal least cost search. It may do the same amount of work, but it should never be the case that it is so misled that it does extra work. If you see that happening, that may mean there's a bug in your implementation. Or your heuristic is not correct, that your heuristic is overestimating. All right, let's go and look at what that looks like on the 8 puzzle. So A star search, same method. The cost is the sum of the cost from start to current state. This is a simple one because all costs are equal, so we're just adding up the number of moves. And the heuristic estimate gets added in, which is how many moves we think we need to do from there. And the heuristic, again, is to count the tiles that are out of place. So our starting state, we talked about this before. The heuristic cost is 3 because the 4, the 7, and the 8 are out of place. Our cost accrued so far is 0. We haven't done anything. So the cost that's used for the priority queue is F, the sum of the other two. So it's basically 3. So we generate the 3 children here. And we have each of these then is one move has happened. So G goes from 0 to 1. The H costs, we calculated those before. What is it for this one? 1 is out of place. 4, 7, and 8 are still out of place. So we have a cost of 4. We have a heuristic cost here of 4. Again, we've taken one move, so G goes from 0 to 1. That means the cost of the leaf as a whole is F. It's equal to 5. It's the sum of the previous two. Over here, our G cost is 1, our heuristic cost is 2, and the total is 3. Notice it's the same total as in the previous step. When this happens, it's often a sign that we're on the right path or we are moving as efficiently as possible toward the goal. Things could happen and this path could fail and another path could become the chosen one. But if you see this happening, then you're like, oh, something good is happening here. The heuristic is dropping as exactly at the same time offsetting the accumulated cost increasing. So we're going to go to this one again. It only has one child. When we look at its cost as a G cost of 2, that's 1 plus 1. And then the H cost here is 1, so we get, again, an F cost of 3. And we generate its children. This child has a G cost of 3. And the H cost is 2, as we calculated before, because the 5 and the 8 are out of place, so we get an F cost of 5. Here we get a G cost of 3, and the heuristic cost is 0, because that is the goal. So the F cost is 3. We choose that one, and we're done. None of the others get expanded because their costs are higher. We just don't visit them. If suddenly the cost had jumped up here for some strange reason, then we would come back and visit these others. The priority queue would put them to the front and they would take over. All right, So we've looked at the nature of greedy best first search. We've looked at the A-star algorithm. We've seen it on a really simple example. In a separate video, I'm going to go through the terrain example, that the same one that we looked at with least cost search, but looking at how A-star might differ from it. And then we will go on from there. So I will see you very soon.